Thanks very much. Does that sound okay? It sounds echoey up here, but it's okay in the room. Okay. Thanks everyone for coming for the end of the long conference. The question, so this is work with my PhD students at Fraser, some of you know. So the question that I'm going to pose and try to answer in this talk is just pretty simple to state, namely, what is the relationship between the precision and determinacy of physical quantities? So we've come to this question by kind of in a backwards-looking fashion, kind of a strange way. But the way we've come to this question is that we've been thinking about spaces used in debates about the metaphysics of quantity, and in particular construing dynamical physical quantities as determinables, which are made of numerically representable determinants on the one hand, and then from the other side, questions about recent discussions in the literature on metaphysical indeterminacy as accounts of metaphysical indeterminacy as applied to quantum mechanics, accounts of quantum metaphysical indeterminacy. And that's got us puzzled about this question. And on first inspection, so I should say, when I wrote this slide, I realized probably I should have added another slide. On first question, one thing you might have said is, these things don't have anything to do with each other at all. So a flat-footed response to this question might be to just say, they don't have anything to do with one another. What is the point of this question? What is the point of this talk? That ultimately, I think, is sort of the right answer to the question. But the way, eventually, to convince yourself that this is the right answer to the question, I think, requires a little bit of work. You don't just get that they're not related to one another for free. So why might you think that they are related? Well, people talk like this. People talk like they are related in the context of, for example, the quantum mechanical uncertainty relations. So when people talk about the uncertainty, they'll say things like, having a precise value of position means that you cannot have a precise value of momentum. Or having, and then sometimes we switch around precise and determinate, and imprecise and indeterminate. So sometimes we say things like having a precise value of this or that quantity entails that you have an indeterminate value of another quantity. These kinds of ordinary language glosses, at least, on what the content of the uncertainty relations are supposed to be, suggest that conceptually there's some connection between these concepts. And we're coming at this from a kind of initially flat-footed stance and just saying, what's the connection? What conceptually, how are these concepts related to one another? So if you want to pull out of those glosses on the uncertainty relation some kind of connection, you would get something like, what it is to have a determinate value of a quantity is to have a value of a quantity that's fully precise. Or what it is for a value of a quantity to be indeterminate is for the value to be less than fully precise. Okay, so that's a naive first effort at expressing the content of the connection between the two concepts, extracted from something like a gloss on the quantum mechanical uncertainty relations. But for that to unpack that in any kind of clear, connected way that's clearly connected to the quantum formalism, we need to understand how to understand these appeals to fully precise and less than fully precise values of a quantity. We need an analysis of the concept of precision. So precision, outside of the context of the uncertainty relations, just precision as a concept, is typically characterized in terms of the dispersion of a collection of values. So if you think about when in high school your chemistry teacher drew the graph with the collection of points which are clustered around the true value but spread, and told you that's accuracy, and the collection of points that are tightly clustered but far from the true value, that's precise. What that's saying is precision is a feature of this collection of values that tells you how much information they share in common with one another. That's a feature of the dispersion of this collection of values. But if you think about the glosses that I was giving you of the quantum mechanical case, that concept of precision, even though we do have an analog of the dispersion in quantum theory, That notion of dispersion of value isn't going to do for making good on an analysis of precision in the sense that I intertwined it with determinacy and indeterminacy on the previous slide. Why not? Well, that is a feature of the precision of a particular value of a quantity. That's what is being appealed to in those clauses. And so dispersion, while there's important mathematical facts about the dispersion of values in quantum theory, we have nice mathematical control over that. If we're interested in this metaphysics of quantity question about how to think about what we mean by the precision of a particular value, we need some kind of new resources. And what I think the natural first place to look, or it's at least the first place that came, I don't know if it's natural, it's what happened in my mind when I tried to think of a way to express what people mean by this. And this also, I should say, Nicolas Gisan's train was delayed, he's going to be here, but also I think I was partly influenced by some of the things that he's been working on together with Fabio Del Santo. And so I got started thinking about trying to characterize precision in terms of the space of values in which the quantity takes its values. So our theories come with a natural standard of full precision. So you might think, okay, there's what it means to be fully precise. It's the one that is fixed by the standard, fixed by the space of kinematically allowed values of the quantity. And for most quantities that we're talking about, that space is R. Not much is going to hang on what specific kinematic space we have in mind here. So that's a standard of full precision that's clearly articulable. And on that way of understanding full precision, it seems natural to say that to have a less than fully precise value, remember we need that as well for getting at what we mean by indeterminate on the intertwined glosses, is to take a value in a space of values that's order embeddable in R. So say the rational numbers, for example. That idea, the idea there is that precision is about specificity of the value, and taking a value in the rationals is less specific than taking a value in the reals, in the sense that there's many real value decimal completions of any given rational value. If I give you the rational value, and then I say the real value agrees with this, but I'm not going to specify, I need to fill in additional details in order to fix what the true value is. Okay. So if you couple that effort to analyze the concept of precision with those initial glosses of the relationship between precision and determinacy, here's what you get. We arrive at the following: for a quantity value to be determinate is for the quantity to take its value in the kinematically allowed space of values in the theory. So if the theory says the space of values in which quantities take their values as the real numbers, to have a determinate value is to be represented by, I would switch between representational talk and dropping it, but I really represented by real number. For a quantity value to exhibit indeterminacy is for the quantity to take its value in a space of numbers that's order embeddable in the kinematically allowed space of values, say a rational number. That's what you get if you just combine these two analyses. But this immediately lands you in a problem, and this cannot be the relationship between precision and determinacy. And the problem is probably obvious. You've probably already seen why this can't be what the relationship is. And the problem is that this naive account makes taking a value in any space that's order embeddable in the kinematically allowed space of values fully precise, and hence fully determinate. Taking in real values fully precise, taking in rational values fully precise, taking in natural number values fully precise. And so if that's what the relationship between precision and determinacy was, we don't ever get imprecision or indeterminacy. And if we thought that there's something to this gloss on the uncertainty relations where part of what the content of the uncertainty relations really is to say that there are values of quantities that, under certain conditions at least, are less than fully precise and are less than fully determinate, and those are somehow related, we need a new tool. We need a new tool for how to think about this. so the failure here is instructive, though, on two fronts. So first, we try to characterize precision in terms of the structure of the space of quantity values. Okay, that ultimately we want to say is a mistake. That's not where precision lives. And I'll say more about what I mean by that in a moment. But second, we try to analyze determinacy in terms of precision. And so the claim we want to argue for is that these two notions do really fully come apart. Those initial glosses of connecting precision and determinacy are, in fact, just misleading ways of talking about something that we can, well, regiment in the mathematics of quantum theory. And the positive view that we want to argue for says that determinacy concerns the uniqueness of value of a quantitative property. It concerns whether, in the theory, we ascribe a unique value to a given quantity, rather than, say, no value or more than one value. And precision, on the other hand, concerns the specificity of a given quantitative property relative to other quantitative properties. So what we mean by that is the place where precision is located is not in the space of values of the quantities. It's not a numerical representation of the values. Rather, it's a feature of the dynamical physical quantities themselves and the relationships that they bear to other dynamical physical quantities in the theory. So in the paper version of this, we worked this out in the context of both the classical quantity evaluation scheme and the quantum one. I'm going to give the quantum one here just because it's more closely connected to the motivation that I've given you, but this is not in the end specific to quantum mechanics. This is an analysis of what it means to have a precise dynamical physical quantity that can be, in principle, applied generically across state-space theories. Okay. So recent discussions in the literature on the metaphysics of quantities have treated quantities in terms of determinables and determinants. I'm going to take a lot of that technology on board and hope that it's at least somewhat familiar. Quantities are determinables, their values are the determinants of the determinables. Determinacy of a quantity is taking the unique determinant of a determinable. So to have in quantum mechanics, having a determinate value of position according to this standard is taking a real number value of position. Indeterminacy of a quantity is failing to take a unique determinant of a determinable. Okay, so that's off the shelf. There's a big debate about this characterization of determinacy and indeterminacy. I'm happy to engage with that debate. It's not the task that we're taking up in this particular paper. We're just taking that analysis of determinacy on board. And now we're really trying to think about the precision piece of the puzzle and squaring it with this analysis of determinacy. So what remains to be done is to provide an analysis of precision that makes good on the claim that the precision concerns not the value space, but the specificity of a quantitative property relative to other quantitative properties. Okay, here's one way to do that. There's various ways in which I'm unsatisfied with this. It's an idealization in various ways of what I think an ultimately satisfactory kind of precision for quantum mechanics could look like. But it's an idealization that I think is instructive, and it makes good on this point that we can locate precision as structure on the space of quantities, not on the value space. And that's what it's here for. So you'll see the ways in which it's idealized as we go. So I'm going to take the determinable properties of quantum theory to be represented by permission operators on the Hilbert space, and the determinants of those determinables to be just their eigenvalues, but more generally their spectral values. The quantum system in a given state instantiates the determinable represented by the permission operator O, just in case O is defined on H. So this is basically saying this is a dynamical physical quantity that that kind of system has. And there's debates about this. David has a view according to which this doesn't happen. We'll talk about that after. A quantum system instantiates the determinant property represented by the lambda eigenvalue of O just in case psi is an eigenstate of O with eigenvalue white. So this is just the eigenstate eigenvalue link, which we take to be a principle that says, given the state of a system at a given time, it tells you which determinants of each determinable property have which determinant values at that time. Okay, so when you take that analysis on board, what you determine, okay, you can argue about each of the principles that I just articulated. Again, that's not what I'm doing here. But if you take that on board, if you agree with all of that, it then becomes a theorem that every quantum system will exhibit what's called gappy quantum metaphysical indeterminacy with respect to at least some of its determinables at all times. You give me a state, I can find some observable which the eigenstate eigenvalue link does not assign any determinant of at that time. Okay. In quantum mechanics, the position operator in particular behaves a little bit funny, and it's also a place where this talk about precision actually becomes quite important. And so let me give you how this works out for the position operator. So there are no position eigenstates, and so the standard position operator is indeterminate in every state at every time. This prescription never assigns unique value to position for any quantum system. But this indeterminacy is not failure to take a value in the real numbers, which are the spectral values of the position operator, the real numbers. They're also rationals in the spectrum of the position operator, but those aren't instantiated either. So this is just very clear that original analysis that I gave in terms of the space of values, order embeddable in reals, cannot be the thing that we're going to hang our precision or imprecision or determinacy or indeterminacy hat on. Suppose we're interested in the position of a particle moving in one dimension. This is in some sense the simplest case where I can show you how this works. Are there less than fully precise facts about that particle's position? Can we come up with some way of making sense of less than fully precise facts? We think that you can arrive at a notion of precision that allows for this by treating quantum mechanical position not as a single determinable property, but rather as a hierarchy of determinables that have a given structure defined on them. So precisification on this view is a relation that generates the hierarchy of determinables. So a determinable A is going to precisify another B, and if and only if, for each determinant of A, each determinant little a of the observable A, there exists a determinant little b of the determinable big B, such that if something instantiates A, it necessarily also instantiates B. So this is the precisification as specificity kind of idea, cashed out in a way which we can translate into quantum mechanics by just saying that a determinable OA is a precisification of another OB if the eigenspaces of OA are all subspaces of the eigenspaces of OB. So if this fact obtains, if the eigenspaces of the determinable O represented by the operator OA are all subspaces of the eigenspaces of the operator represented by the operator OE, then whenever something's an eigenstate of the former, it will also be an eigenstate of the latter. So I have to change some of that. And that's the sense in which, so whenever I have a determinant of the first one, I'm always guaranteed to have a determinant of the second one. Okay. So we want to cache out precisification in terms of this structure. I'm going to draw you a picture in a second that will make this less opaque. And suppose the space in which a particle moves is represented as the real number, so a particle on a line, and we're going to let P, capital P, be a partition of the line into intervals. I was going to draw on the board, but I think I'm going to go over here. So I've got, hopefully this is at least somewhat legible, of course, not particularly, but let me see what I can do.
Try one of those on the other. Try one of those on the other.
Ah, good idea. Okay. So here's my line in which the particle is moving. Is that a bit better? Okay, great. So here's the line in which the particle is moving. I can partition this line in a lot of different ways. I can partition it by just splitting it into two intervals. I can coarse grain it more finely, and so on ad infinitum. We're going to assume that our partitions are uniform. And now, here's the idea. So there's, for each partition like that, for each big P, there's going to be a self-adjoint operator, which we can write like this, where this big pi on A is the projection onto the region A. So the region A is going to be one of these cells in one of the coarse-grained elements of the partition. And lambda A is a cooked-up eigenvalue thing for the projection onto that region. Okay, so those operators are what we're going to call region determinables. And now, if a partition P prime is a refinement of the partition P, then OP prime is going to be a persistification of OP in just the way that I specified. So what that says is, if I write down, I've constructed an observable for this partition, and this OP is constructed an observable for this partition, and this partition. What this says is, this observable persistifies this one persistifies, and in fact everything above it. This one persistifies that one, and everything above it. What you find down at the bottom, where the coarse graining becomes maximally precise, is just above the points in the line. This corresponds, what you get at the bottom of the partition is a new operator by this construction, which is just the ordinary position operator. Okay. Good. So this just kind of like captures in a little bit more detail what the nature of these determinables are going to look like for specifically articulated partitions of the line. So if I take the P to be the partition of R into unit intervals, say, there's a region determinable associated with P given by this guy. The nice thing about this construction, and the reason we've produced this particular construction for a particular coarse graining, is that now we can write down, in fact, a refinement of P, the partition of the line into unit intervals, which divides each interval in P into 10 intervals. So it's a coarse graining of the unit intervals with each with 10 cells. And its associated region determinable is going to be given by this guy. So this is just the same form as the previous thing specified to that specific partitioning of the line into cells. Why worry about this? It seems like kind of a weird ad hoc, oddly specific construction given the kind of thing that we're doing. Well, think about the numerical values that this kind of scheme is going to generate for the eigenvalues of being located in one of these things. So let's say that this is our unit interval guy. That's going to say that, depending where we put the origin, that'll say that the eigenvalue that you get assigned if you're located here is 1. The eigenvalue associated with being located here is 2. The eigenvalue associated with being located here is 3, so on. Okay? So we just assign the natural numbers as the eigenvalues. So according to the scheme that I set out at the beginning, what that means is that if a system has a state according to which it's fully localized in, say, this cell, the eigenstate eigenvalue link is going to assign it for its value of this region determinable, the value 2. It's like the coordinate position of the particle is labeled by the number 2. Now, if the state of the system is in fact more sharply peaked around the specific region, such that it's contained not just in this unit interval, but in fact is contained in one of the cells of the finer partition one step down in the precision hierarchy, what we'll find is that, I haven't imagined there's 10 cells here, and imagine that our state has the system peaked really sharply, sorry, I should draw bigger, and such that it's actually located all the way here. The eigenstate eigenvalue link is going to pick out the eigenvalue corresponding to the projection onto that region and none of the others, and so it's going to give the value, ta-da, 2.1. Okay, and we can go on all the way down the precision hierarchy, and what this construction does is it just says we can make sense of this talk of assigning more decimal places of precision as the position of the particle in a way which is completely captured by the what we take at least to be the orthodox quantity evaluation scheme of quantum mechanics. All of this kind of like background stuff about precision can get loaded in to a careful construction of what the relevant region determinable properties of the system actually are. And okay, so I've got just a few minutes left, but I think that's about what I wanted to say. A general expression for the class of quantum reasonable determinables associated with the refinements of P of this form, we can write as shown here. Increasing values of K are going to result in determinables composed of projections onto elements of finer partitions of the line, and hence determinables that precify region determinables generated by smaller values of K. That's just to say that being located in one of these relatively very fine partitions down here, being in an eigenstate of one of these projections of this region determinable is a more precise way of being located than being in a state where the most precise location fact is that you're an eigenstate of one of these higher up in the precision hierarchy region determinables. Okay. And so that is as I warned you at the beginning, a very idealized construction. This whole coarse graining thing is artificial. The numerical assignment of values is generated to kind of imitate a certain way of thinking about numerical assignment of values to positions, which is not, in the end, really, we think, central to the right way to think about this. The reason that this construction is, in fact, important is it gives us proof positive that we can do the thing that I suggested at the beginning, which is we've generated a partial order on the set of determinables. We've generated a partial order not on the values that we're assigning to the locations, but rather to the relationships between the quantitative properties that we assign to the system. Okay. That partial order constitutes the hierarchy of the precipitational hierarchy that I was referring to earlier. And I already said that in the limit where the partition becomes arbitrarily fine, the region's determinable is just going to be the standard position operator. Okay. So I'm nearly out of time, but let me just say that what that oddly specific, admittedly idealized construction gives us is proof of principle that we can let precision and determinacy come completely apart from one another. Determinacy, as I suggested, we just take off the shelf from recent debates about determinacy in the quantum metaphysical indeterminacy literature and say that's an issue about the uniqueness of value. And then precision, on the other hand, concerns the specificity of a quantitative property relative to other quantitative properties. This schema makes good on that second clause. It says we can treat the precision of our dynamical physical quantities as a feature not of the value space, but rather as a feature of the collection of dynamical physical quantities. Okay, thanks.
Now we have comments. Cristian? Yeah. Christian? Can you hear me? You need my. Okay.
Yeah, thank you for the talk. I'm really on board on everything. I really enjoyed reading this paper by Patrick and Mike. So I sent the author of the comments a few days ago, just asking for a couple of clarifications on background issues and methodological issues. I guess we are largely in agreement, so I just wanted to say a few things more maybe on a couple of topics. The first thing is, in the paper especially today, a little bit less, but in the paper especially there is this mention of kind of a default view, or maybe better, a view that some people may have as regards to the connection between intuitive, let's say, connection between imprecision and indeterminacy. Of course, I think their job is great in explaining why they differ. So I wonder why would someone actually think that they have anything in common? In the description of the default view, so 2 points on this. So in the description of the kind of default view, I was thinking that maybe Giselle comes to mind in kind of making this mistake of conflating the two notions. It was Giselle. But usually the people in the quantum indeterminacy debate, and for instance the people that, like Jessica Wilson, that they are kind of using to develop their account, are quite clear in distinguishing the two notions. So for Jessica, again, the uniqueness requirement for determinacy is substantiated by a determinable, it's stated quite clearly. So then I thought maybe other kind of views, here we have Alessandro has a different view, there's also other views like Lance and Williams. Maybe for them, this conflation is actually something that goes on. I have to think a little bit about this. In the Bunsen-Williams approach to indeterminacy, it is true that they have this idea, I'm not going to go into detail, but they have this idea that indeterminacy is this kind of worldly unsettledness between precise options. So they have precision in a way in the definition. But I think you can do without, and I think, or at least you can even define precision in another way in their account. So I just wanted to know what's the target that you have in mind. The other thing I wanted to say is more general about motivation for kind of unifying these family of notions. So it is true that you gave a very nice case in point where the two are distinct. But I think some people may be tempted to say, okay, but maybe when we speak about indeterminacy, we have some kind of pre-theoretical notion in mind, and our best shot would be to try and formulate an account that kind of unifies different phenomena, such as open future, indeterminacy, quantum indeterminacy, and maybe imprecision. Here, a quick note. So sometimes this goes wrong, in my opinion. Like, for instance, Jessica Wilson tries to apply her account also to the open future case with kind of dubious success. But still, I think the general idea of trying to unify is something we should have in the back of our head. So one thing that's mentioned in the paper related to this is the distinction that Mike has in another previous paper between epistemological and imprecision and metaphysical imprecision. So of course, as I said earlier, why would you think that epistemological imprecision has anything to do with metaphysical indeterminacy? But if the kind of imprecision we have in mind here is the one that Mike has in his previous paper from 2018, or the imprecision, then if the imprecision we have in mind is metaphysical, then I guess the question is actually, maybe they, you can wonder whether they have anything in common. Only last one is about the Gatti and Gatti distinction. So you seem to assume in the paper that there's no difference here between having a Gatti implementation or a Gatti implementation. So a Gatti implementation is the one where you have no determinant at all, corresponding to a determinable, and the Gatti is where you have more than one. And it seems though that all the cases that you have in mind are Gatti, sorry. So I wonder whether one that would want to push the idea that maybe they have something in common in the metaphysical sense may go in the direction of saying maybe what's different is that in the imprecision case it seems to be only Gatti. I'm just curious about what you hear. And again, thanks for the paper, it was great.
Thanks, Cristian. So let me just briefly try to touch, I think, on each of those points, though I'm not sure I'll be able to adequately address all of them quickly. On the Gatti and Glutty front, we focus on the Gatti business just because on the way we're thinking about the quantity evaluations given quantum mechanics, it turns out to be a theorem that the indeterminacy in question is gappy in a strict mathematical sense. I think there's, in a connection with another one of your points, I'll come back to a place where I think maybe a glutty thing could come back in, but that's why we're just focused on the gappy instances of the phenomena. And on the unification front, I think, yeah, we're understanding the precision, we're after a notion of precision that's like pretty tightly tied to the quantitative structure of the dynamical physical quantities, because that seems to be what's required in order to pull apart these kind of glosses that I started out from at the beginning in terms of the way people talk about the uncertainty relations. I'm perfectly, yeah, like unification is great so long as it doesn't come at a cost. And so I think we've been thinking, the way we've been thinking about the project is pretty tightly constrained to this specific task of the conceptual analysis of precision as relating to indeterminacy, where the notion of precision at issue is this notion tied up with the quantitative structure of the properties and these kind of like distinct epistemic and metaphysical glosses that you get on what that imprecision might amount to. So that brings me to that point. I think ultimately this kind of tool, this kind of rethinking of where precision lives in the structure of the dynamical physical quantities helps to think through what we might even mean by what I was talking about in that previous paper. And in fact, if you look at that paper, you can see me kind of struggling to come up with a surrogate for precision that doesn't fall into this collapse problem that I pointed out towards the beginning of the talk. So in some ways, this is an effort to build the architecture required to fill in a non-silly version of the metaphysical reading of the kind of indeterminacy there. So this really is like an effort in that direction. I do think ultimately there's going to be a way back to the more epistemic glosses that people give on precision. So things like the dispersion of values kind of view of precision. And I've stated things in the talk a bit more starkly than I expect the situation to be eventually in the final analysis. So in the final analysis, I think there's going to be versions of imprecision that are mathematically equivalent to the kind of construction that I'm giving here, which are characterized in terms of the value space. And what you're going to have to do to arrive at that kind of thing is to do exactly what people do when they talk about epistemic imprecision, measurement uncertainty, and things like that. The way I understand what people are doing when they talk about measurement uncertainty is that they assign interval value to a quantity. And so if you're coming from the metaphysics of quantity kind of perspective, where the kinds of value spaces that we consider are numerical values, that looks prima facie puzzling. That value space has, the elements of that value space have more structure than the kinds of things that we normally associate with value spaces in the context of the metaphysics of quantity. But I do think that ultimately, at least on an epistemic reading, there's going to be a mathematically equivalent version of this. And there's it's not just the interval value ways of talking about this. I think there's going to be others that actually recover this sort of construction mathematically as well. This treatment in terms of the precision as a hierarchy on the space of quantities strikes me as most natural when we want to give it a metaphysical reading. In the case of the epistemic stuff, I can kind of make sense of value spaces that have more structure. In the metaphysical reading of the indeterminacy, it starts to get quite difficult for me to know what it would mean for the value space to have interval values and things like that. And but there's a big space of possibilities to consider here that I haven't discussed yet in the talk. And then the last point, which I think is the one that you're very right to press me on, is just what is this default view? And it's default in the sense that people talk like there's a relationship between precision and determinacy when they talk about the uncertainty relations, and the precision talk that they're engaging with is precision of particular value, not a collection of values. And the view I gave is default in the sense that, to my knowledge, there isn't an analysis of precision as a feature of individual values in value spaces. And so it's defaulted to in the sense that it is the thing that strikes me as like tracking the way that people use the decimal places of precision talk in an effort to give an analysis of more or less precise values. Having a more precise value is having more decimal places of precision. But this, you don't have the more structured value space of intervals collapses into full precision, full determinacy. So that's the sense in which it's default. But you're also right that simultaneously while this was starting, we also were corresponding with Nicola Gizan a bit about some of his work with Claudio Del Santo. And I think in the end they have a strategy to avoid what I'm calling this collapse into full determinacy problem, but it's because the numerical value space that they use is complicated. It's also got more structure than a space of numerical values. And that so they have a trick for doing something like what we're talking about doing in terms of the value space. But again, that's a view where you put a whole bunch of additional structure on the value space.
All right, thanks.
Yeah, sure. So I'm trying to understand the theory, or better, the distinction between determinacy and imprecision. Suppose we have our two observables, OP and OP prime, where OP prime is the finer of the two.
Mm-hmm.
Suppose I make an observation for OP, and the wave function collapses, and I know that my particle, whatever, is in a certain region. Okay, but that doesn't give me any information with respect to OP prime. So I don't know whether it's on the left or the right side of that slot.
Correct.
Okay, so you would say that this is a case of precision up to OP. Is that how you would characterize this situation?
Yeah, so I mean, the situation you just described involves both precision and determinacy, but they're analyzed separately. So if in the situation you described, this you conduct a measurement with this, that's a projected measurement of the observable OP, like you're asking the system the question, are you on the left-hand side of space or the right-hand side of space? When you ask a quantum mechanical system that question, you know that it's going to give you an answer, yes or no, to one or the other of those things. Those are the 1 or 0 eigenvalues of these, of the projections for the cells, not for the region determinables, right? So when I do the measurement here, I'm guaranteed to get one of these eigenvalues. The eigenvalues label membership in these cells. So I'm going to get determinacy of the observable OP prime, assuming that the measurement isn't somehow like over sharp or something. You really just measure OP. I'm going to have indeterminacy with respect to every subsequent determinable in the region determinable precipitation hierarchy. And so there's always going to be, for any given measurement, there's always going to be a lower bound to how precise the precision facts about the particle are, characterized by which observable you have U of R and eigenstate of. So so like precision is the precision of the measurement, you might want to say of the measurement or of the location fact that the measurement gives you is a feature of like which of these more or less precise properties the system has a determinate value of. But the sense in which something's more or less precise is cashed out in terms of the relationship between these properties between each other.
Great. So just to wrap it up, in any of these cases where I have a bound on precision, I also have indeterminacy, right? So there cannot be cases of imprecision without indeterminacy.
In the case that I've given you here, we have this boundary constraint effectively in that no measurement can, there's no projective measurement on the least element of the partial order. And so there's no position eigenstates. And so every quantum state at every time exhibits indeterminacy with respect to the standard position operator. In this way, we're talking about determinacy and indeterminacy. And so there will always be indeterminacy at the bottom, and there will always be imprecision. And so there's always a lower bound on the precision.
Yeah.
Patrick has a picture on this.
Yeah, so it seems like, so if I understand where you're going with this, is sort of say like, okay, well, they're sort of distinctly analyzed concepts, but they're nevertheless necessarily connected to each other in some way. So
This in one direction, it seems to me. So if you have imprecision, then you have indeterminacy. But the idea that if you can get all the way to the bottom, I assume that means that you cannot have a finer partition, and so that it cannot be more precisified, and so you have precision.
Yeah, I mean, you would have to come up with the observable that has a value space that somehow got more spectral elements than the rails, which is we don't really consider in quantum mechanics.
yeah.
Question I'm not sure that I understood what you say, but would it be correct to say that indeterminacy is relevant or applicable in quantum mechanics, but precision and imprecision also applies to classical physics?
Yes, so I can repeat this analysis. So, good. So this is, sorry, I didn't mean to cut you off.
And the other question is even more simple. So these are operators, but they all correspond to measurements of practical ways of making measurements.
Observable properties, yeah. That's true. So everything here is an observable property in the sense that they're self-joint operators, which represent things that are physically measurable in quantum mechanics. That's true. Those are the only kind of representatives of dynamical physical quantities in the state space of quantum mechanics, and so that seems like a great place to locate the analysis. On the first point, you're exactly correct that there's nothing like I mentioned briefly in the paper we do this in the context of classical mechanics. The exact same analysis can be applied to any evaluation scheme, and so you might wonder like why think about this in the context of classical mechanics where the valuation scheme doesn't have indeterminacy. It's a theorem there that in every state, every system has full determinacy with respect to all of its properties that are represented on the state space. Why think about indeterminacy and imprecision? Well, even in a theory like that, we want to have representational resources for thinking about making imprecise attributions of properties to systems. We do that all the time. In fact, any non-ideal theory of physical properties is going to have, in some sense, the resources to do stuff like that. And so, I think you can repurpose this way of thinking about what the content of precision is to do exactly this, to think about what we might mean by ascribing imprecise positions to classical mechanical particles, despite the fact that all of those things are fully precise. One thing that's funny when you do that is that here I haven't introduced any properties that don't already have mathematical representatives on the state space of quantum mechanics. Everything I propose to here is there waiting on the shelf for me to build my special coarse-grained region determinable properties. In classical mechanics, that's not true. In classical mechanics, when I just repeat the same construction, analogs of what I'm calling OP prime, OP double prime, etc., require writing down discontinuous characteristic functions, which aren't the kinds of functions that represent observable properties in classical mechanics. You might wonder, what to make of that. But if you're willing to expand how we represent properties on that state space and allow for these discontinuous characteristic functions, then you can use those as representatives of things like imprecise location facts about classical particles, even in cases where the theory ascribes fully determinate positions to those things. There can still be imprecise facts about them, despite them being fully determined facts as well, and fully precise ones. Yeah.
I'm going to abuse my privilege and follow. I just wanted to combine those last two questions. So, wouldn't it then follow if we had an imprecise location fact in the classical case, we would also have a determinacy about further persistifications?
No. So the way I'm talking about an imprecise location fact is imprecise means less than whatever the theory countenances as fully precise. So even if imaginarily in quantum mechanics there were eigenstates of the position operator, that would be the fully precise position fact. There happen not to be such. But if there would also be facts about all of these imprecise position determinables as well. And there's nothing deeply mysterious about that, I don't think. It's just like there's a load of properties encoded on the state space of quantum mechanics. They enter into really structured relationships to one another in terms of what they're telling you about the system. And I'm kind of unbothered by the conclusion that even in a case where there are fully determinate, or fully precise, sorry, I keep doing the thing I shouldn't be doing, even in the case where there are fully precise position facts, there continue to be imprecise position facts as well.
So there would only be indeterminacy if there were only imprecise.
When there's a bottom to
only
the...
imprecise position facts.
Exactly.
Then you would have...
Yeah. When there's a lower bound.
We don't think that's the case in classical.
The the rules for ascribing values to dynamical quantities make it such that it's a theorem that there never are such values.
Peter?
Yeah, thanks, Mike. That was excellent. I think I'm totally one of your distinction. My question, your answer to Alexander partly was my question, you were saying precision and determinacy come apart. Yeah, sure, they're related. You said that they were related in your answer to Alexander. But I thought maybe you could elaborate a little further. You started out by using the example of the uncertainty relations, and you said, look, people talk about them in determinacy language, and they talk about them in precision language. What's the right way to talk about them?
Yeah, so that's part of what we're trying to do here. So let me take a stab at it. It looks like Patrick has a finger on it. So partly the trouble with that talk, or what we don't like about that talk, is because of this phenomenon that there's no position eigenstates. We're always imagining a scenario where we've done a projective measurement of, say, position or whatever, which doesn't exist, and then we're saying there's this maximal, in some sense, imprecision in the momentum facts. But this is really artificial because, so what we want to move towards is a picture where if I've got, so we want, in the end, what this should spit out is a reinterpretation of this kind of talk about the uncertainty relations. That's what we're kind of driving at here. In the projective measurement case is just inherently limited because of these issues, and ultimately I think it's not the right language to try to give a fulsome story, and you need POVMs, so that's coming down the pipeline. But all of this, we think, can be translated into the language of POVMs, and then you can really talk about measurements that are sharp in this way. But the right way, well, maybe Patrick, you want to jump in?
Well, so without going to POVMs, you can't really say anything that's super compelling about the uncertainty relation. You can say something that's not super compelling, but still sort of schematically informative. So in the projective case, it's a fact that if two operators don't commute, then you can't, how does this work? If two operators don't commute, then saying that there is determinacy above some level in the precision hierarchy for things related to one of those quantities prohibits there being determinacy below some level in the corresponding precision hierarchy for the non-commuting interval. So that's a theorem we can prove. And in the projective case, that sort of smells a little bit like the uncertainty relations. Now, it's not the uncertainty relations because those are concerned with variances. They're not concerned with the eigenvalue link as such. They're concerned with features of the distribution. And it's sort of capturing the sort of richer quantitative structure of uncertainty relations that you can't get from the projective picture that requires going to TOEMs. But you can still get a sort of very rough and ready schematic view of it, even at this level. That's kind of the thing I want to add.
Yeah, that's where we're headed.
Yeah. Okay. Quick follow-up.
I'm sorry, it's not like it's a question.
Oh no, it's a quick question. Go ahead.
Okay.
You last question.
Oh, right. Okay, cool. Just, I'm not sure why we should accept the finally maximum specific level in points, actually. Does it actually fit into the mathematical structure you really do expanded now? Since that the decision makes this actually, this is why I should think that the points that you got should be included in this hierarchy and like it's a maximum specific one. Actually, these various regions that can be, systems can be specified, so it's also a region that is not. It's not clear to me why the point should be maximum specific.
Yeah, so the reason that they are is just because I'm following the letter of the law of the determinable and determinate specification rules that I set out at the beginning, and I was appealing to those when I said this or that is a theorem about whether there is or is not indeterminacy about. And in particular, what the determinate specification rule that I gave you said was that the determinants of a given quantity are their eigenvalues, or more in this case, their spectral values. The spectral values of the standardly constructed position operator in quantum mechanics, which is what lives at the bottom of this precipitational hierarchy, are real numbers. And so there's various things you might want to say here. You might want to say, like, look, some property that, some dynamical physical quantity that can't take a value in any state, like, is not a physical quantity or something like that. Yeah, it's a funny situation. What's weird about, so suppose you went for that kind of view. That starts to get weird in a different direction though, which is that we write down the dynamics in terms of that dynamical physical quantity. So now we're saying this is like a dynamical physical quantity that generates the dynamics of the system, but at the same time it's not a dynamical physical quantity that the system can have. I think the best thing to think here is probably that this is just a kind of ideal, like this is always an idealization, the fully projective thing, and you need the tools of TOEMs to be more careful about what the real physical properties are.
All right, we're going to leave it there.